Good afternoon, everyone. Thank you all for coming. Welcome to section B of this course. Or I don't know, maybe you should welcome me because I'm kind of new to the course compared with you. Yeah. Well, in fact, before just jumping straight into the tutorial, so a few comments on this part of the course. The material balance or mass balance part of it, of course, involves actually convection and diffusion. And we'll be trying to gain experience in understanding the different geometries in which convection and mass transfer can occur. And these are important precursor concepts for your reactor fundamentals and your applied reaction engineering, also for mass transfer and so on. So in the earlier courses, it was rather fundamental. So looking at the relationship, the equilibrium relationships among your chemicals in the system and so on. So in this section of the course, we are trying to understand how material transfers across a fluid. So largely as a result of concentration differences across a fluid, and also as a result of the bulk movement of fluid, the concentration may vary across a space. So if you think of a tube, and if a fluid is flowing along that tube, then you may have significant concentration differences across that tube. And that may complicate your efforts to model that process unit. So for example, a tube may well be a reactor. So if you have some kind of variation across that reactor, if you've got concentration differences across that reactor, then that will make it more complicated for you to estimate the overall reaction rate. So of course, it would be nice and easy if we had one concentration for the whole tube. Then we would just use something like reaction rate expression and say, my reaction rate in this tube is this value. But if your concentration is varying across that whole space, then we have to do some kind of averaging to estimate the overall reaction rate. And of course, we can only do that kind of averaging if we know exactly how that concentration is varying across the space. So that's just one example of the relevance of our material balances, right? So the material balance doesn't just give us the total amount that's changing in the system. It tells us how the number of moles and how the mass of the system is distributed across the space of interest. And the space could be anything. It could be a tube, like we mentioned. It could be a slab. It could even be a flat sheet of something. So in these material balances, we are going to develop the relationships that will help us determine how the concentration varies across the space. So across the space and also across time. So if you take some small volume, so if you take your fist, right, you may have a concentration variation inside your fist. So the, whatever's in your hand, whatever chemicals are coated on your hand, maybe your, I don't know, well, I won't try and speculate, maybe your hairspray or whatever. And then there's a concentration variation inside your hand. And so in 3 dimensions, that concentration is varying. And also that concentration is changing with time. So if you imagine there's a certain volume of concentrations at one time instant, then of course there's diffusion out of that space. And so over time, that 3-dimensional description of concentration is changing also. So when we are able to predict this variation in both time and space, then it becomes possible to predict how a unit is going to perform in time. And you'll see this in many, many different ways across the upcoming coursework in the chemical engineering program. So I've mentioned the reaction engineering, mass transfer. It's also in design. It's pretty much in everything. So like the title of the course suggests, these are the very fundamentals of chemical engineering that spider out into all these areas. So spending your time on really understanding quite deeply in this course is a very useful thing to do. It's going to stand you in good stead for the rest of the study in the degree. And I will say, in a sense, there is enough time in this course. So conceptually, there are maybe 4 or 5 ideas. And if you are able to interface with those ideas well, if you engage with them well enough, really think deeply about them, it's going to make a big difference to later on when you're, for example, trying to estimate what the reaction rate is in the tiny little particle, which is sitting inside a big reactor, and across that whole reactor, concentrations are varying, and in the particle, even concentrations are varying. And of course, I've been saying concentration all this time, but the evolution of concentration varies also in terms of the other state variables. So your temperature is another important state variable, which may well influence how your concentration varies across the space. So, for example, and I must in a way apologize because I often use reaction engineering. That's my research area. I forgot to introduce myself. My name is Randi Rawatlal. I've been working in the field of reaction engineering for the past 20 years. More recently, I've switched over more to data science and artificial intelligence and those kinds of topics, but always come back to reaction engineering, because the concepts that we learn there are so applicable to virtually every area. So there are parts of the modeling that have to do with ages of populations, and so you'll be surprised how much of your chemical engineering fundamentals can be applied in many other fields, which would never dream of saying they are related to chemical engineering. Okay, so I hope that has motivated some of the material balance interests here. And I guess we can go straight into it. So looking at, to have a look at what we are saying here, or what's in this tutorial. So these three questions, of course, there are three questions there at the moment. So we'll be looking at question 1 in some detail. Question 2 is simply calculate the diffusivity. So you are given the correlation. So this one is just plug and play for your numbers. I don't mean to dismiss it. Being able to estimate the diffusivity accurately is an important thing to gain some experience with, especially because there might be a bit of wrestling with the units to do. So please make sure you do attempt this question 2. And then question 3, so I've substituted some new questions in. So that's because actually the original question 3 here mentions an O-ring production example, which is something you won't be able to tackle just yet. So I've put in these other questions which are increasing in difficulty. So it starts out with a fairly simple situation, which you shouldn't have much difficulty working on. And then each question progressively builds the difficulty so that you are able to solve this so-called O-ring production problem more easily. So these are the ones that we want to spend some time on today. And in fact, I will say these questions, as I started putting them together, I really tried to create a sequence that would give you quite a lot of experience in the majority of modeling that we'll do in this course. And so these problems, if you like, are kind of seminal. And if you spend a good space of time on these problems, you'll likely be able to do quite well in the rest of the course. So these are problems, we won't be able to get through all of them today. Over the coming weeks, we'll develop these quite deeply. So it's important to realize these problems will come back repeatedly across the course. Anyway, for now, let's get into this question 1. So let's just read it first. So it's saying here that we have a component diffusing in the Z direction in a stagnant fluid. And in fact, even in that one sentence, there are a number of things infer. So let's start sketching this out first and trying to keep track of all the information that will come. So we have some fluid, and it mentions that there's flow only in the Z direction. It doesn't say anything else about the type of coordinates that we have. It doesn't say polar or Cartesian or spherical. So let's just assume these are Cartesian coordinates to begin with. And so let's just sketch out our axes. Let's see, and the right-hand rule applies, right? So if you've got X and Y, then Z will be sticking out of the page. But I actually want Z to go in this direction. So I'll want X going that way, Y going there, and then I've got Z there. So X is up here. And by the way, you should be that careful in this course, right? Being able to keep track of your dimensions and your directions is quite important. You have to get that right if you are going to write balances across complicated geometries and so on. So yeah, it's pretty shaky here, but that's X, Y, and Z. And now we've got some fluid that's varying in Z. So let's just draw something, some kind of space here. And so we've got a fluid that seems to be diffusing in the Z direction. Right, so this is Z. So always make a small sketch, keep track of your directions. And we are told it's a stagnant fluid. So the fluid itself is not diffusing. So let's just draw something to imply a solute or something like that. And you've got your component A, which seems to be diffusing through that. So stagnant fluid containing component B, in which each condition in turn applies. So we can't have these two occurring simultaneously because these are different situations. It's saying, number one, component B is in equimolar counter diffusion with A. And then in part B, it says the flux of B is 0. So we are given quite a lot of information. We are told that at Z equals 0, you have component A in a mole fraction of 0.5. So we can define a point here and say at this point, we've got Z equals 0, and the mole fraction is 0.5. Why do that? So XA is 0.5, okay. Okay, so that's one piece of information, and then the other one is that we've got some point a bit at some distance along. So at this point, we've got that. Oops. So this is X A equals 0.5, and then we've got a different point here. We are told that at a distance of 1 meter from that point, we have a different mole fraction, 0.85. So we've got here Z equals 1 meter. And at this point, we have XA being 0.85. Right, so we already know some mole fractions at these 2 points. And now we would like to know what's going on in between. So if we look here, it says, so the information, we are given the diffusivity, so the constant in your diffusion flux term, that's known. And then the total concentration is also known. So in your fluid here, we can identify a total concentration. If you take all the moles divided by the total volume, that's 50 cubic meters. So just to make that note, this C equals 50 moles per cubic meter. Okay, so that's the situation. And we are asked to develop expressions for the mole fraction of component A. What's the molar flux in each case? What's the mass transfer coefficient? So in this first case, it's equimolar counter diffusion of A. So we can say here equimolar counter diffusion. That implies to us that the molar flux of A is equal to the molar flux of B, but in the opposite direction. So we just use a minus sign to say it's in the opposite direction. So of course, molar flux is a vector quantity. So if you just stick a minus sign in front, it switches the vector onto the other side, and so that's how we can represent equimolar counter diffusion, right? And so we want to now develop an expression for the mole fraction of component A, given this piece of information. Well, if you followed the video lectures that are posted on YouTube, I, at some length, derived the molar flux of component A. So I'm just going to look at it in my solution here. So if you follow that earlier video, we found that the molar flux of a component will equal its diffusion flux plus its convection flux, where we estimate the convection flux as the mole fraction of that component multiplied with the total molar flux of all the components in the system. All right, any questions or comments so far? Is that an old hand, Nkululeku?
Yes, yes.
Okay, thanks. Okay, so that's our total molar flux. And now we've got equimolar counter diffusion. So clearly Na plus Nb is going to be a 0. So we can forget this whole term, leaving us with just this part. And so if that's what we have, then we can say that at steady state, our molar flux, separately to that, unrelated to this equation, we have to acknowledge that for us to be at steady state, we must have the same molar flux across the whole space. So we anticipate that our, our concentration may be varying across the space. We are not saying the concentration is the same everywhere. And in fact, from the specs of the question, you can see that the concentration is not the same everywhere. But at the same time, the molar flux could be constant. We know the molar flux is not 0. We know there is a concentration difference of component A. So there is going to be a net molar flux, which is not 0. But at the same time, that molar flux could be a constant number. And in fact, if we want, if the system is at steady state, right? If we have a steady concentration of component A, so I'm just going to sketch, well, now let's use the A color. So there exists some concentration of component A across that space, right? We don't exactly know what it is yet, but let's say it's something like that. And and now we want to know with steady state, how does this, what does this look like? Now at steady state, we have to have the amount of A at each point in the system being constant. The molar flux must be constant. So I'm just going to draw that. So let's imagine this. So let's just draw a couple of partitions here. So now imagine the situation where you've got a certain molar flux here. So A is fluxing at a certain value here, and then it's fluxing out here at a certain value. Now in this space, in this middle panel here, the amount of A in this space will remain constant in time if and only if these two fluxes are equal. Right? If this flux is greater than this flux, then A will rise in the space. If this flux is greater than this flux, then A will drop in this case. So the only way for this system to be at steady state is if these two fluxes are equal. Right? So the same argument can be applied to all regions across that tube. So that means NA is a constant with respect to Z, right? So your molar flux of A is constant across that whole space. And a way to represent that is just to say NA is not equal to, no, not equal to, so it's more of a computer way to write it, but anyway, NA is not a function of space, although the concentration we know is going to be, well, we think it may be a function of space. So the concentration might vary across the space, but the molar flux may be constant. And especially for it to be at steady state where this concentration profile is steady, the molar fluxes have to be constant. And so here we need to be a bit more specific. When we say constant, we typically mean time. So in terms of time, our concentration is going to be the same. So for all time, you are going to get the same curve. So if you look at this tube, right now, it may have this curve. And then if you look at it 5 minutes later, it's going to have the same curve and so on. So the thing to notice is this concentration is not constant in space. So across Z, it's varying, but it is constant in time. And so, like we said here, the only way for it to be constant in time is if your flux is the same in space. So your flux is equal at all points in Z, and that leads to concentration being constant in time. Okay. So once you have those, and you might think I'm going on and on about this, but you see, once you have those basic ideas in place, then the rest of it is just mechanics. The rest is just a matter of applying these things to your equations. So we have that the molar flux is a constant with respect to Z. So now that we know this is a Z constant, we can say that in this equation, if we want to integrate XA with respect to Z, we can just treat this as a constant. We know the total concentration is a constant, and then the diffusivity, it's just given to us as one value. So these are all constants. And so dXA dZ is equal to a constant. And so you can just integrate this and you get a form like this. So this tells us then that our system has a linear dependence on Z, right? And so if we were to draw that, then we would say we've got one concentration here at which is corresponding to 0.5, and you've got another concentration there, 0.85, and the concentration profile simply looks like this. Right, so that's the first question solved. Your concentration profile as a function of Z is a straight line. Any questions or comments so far? Okay, so that was the result we got, specifically if we have equimolar counter diffusion. So only because that term disappeared did it stay nice and linear like that. Right, the next part of the question says, right, so just going back here. So part A is what we solved there. Then the next part says, what if your component B's net flux was 0? So if NB equals 0, so it's no longer equimolar counter diffusion. So if NB is 0, then this equation simplifies like so. So that's your new equation now. And you've got NA on both sides here. So you can take this XA, you can take that across and group out for NA. So that's there, and then that's what's left over on this side. And now, still the same argument holds. The molar flux is still constant, right? So this we are still talking about steady state. So in the question we were asked, what's the steady state concentration profile across the reactor? So for this to be steady state, for the concentration to be in its steady state, as we said, the molar fluxes must be the same across the whole space. So Na is a constant. And so if it's not a function of Z, then we can just treat it like a constant here. And so we can integrate it like so. We can separate our variables. Of course, you've got XA, you've got a function in XA here. And then these are not functions in XA. Your total concentration is not a function of your component mole fractions, and that's your diffusivity. So you can divide by 1 minus XA, and then take the dz across there, and then just integrate this. So here, of course, it's 1 over the variable. And so the integral of this is going to be the log of that function. And then there's a minus sign, so we take out a minus sign as well. So log of that function, and then the minus sign. And actually, we had a minus sign here, so there's a minus sign. But I see here I've reversed the z's. So when you integrate this from z1 to z2, you would normally write z2 minus z1. But I've written z1 minus z2. So that's why that minus, the extra minus that comes from the integration, that's where that went to. It went to reverse those things. And so you can rewrite the equation like this. Right, so that's what we can use to find out the molar flux, right? And so yeah, I should mention here. Okay, I just want to write some notes here on this. So right here, let's see, how do I? It's taking up a bit of screen space. Okay. All right, well, let's just do that. Okay, so here I just want to say that when we integrate this equation, we seem to have chosen specifically Z1, Z2, and XA1 and XA2. Of course, Z2 and XA2, we could have chosen those to be any numbers along the way. So what we'll say is that if you integrate this equation, you can more generally say NA as a function. So NA as a function, not NA, NA as a function of Z. So NA Z sub 1 minus Z equals C times DAB. C DAB ln, then it's 1 minus, and I'm just going to call it XA. This is 1 minus X sub A1. So, oof. Sorry, this is getting messed up a bit. So that's ln of 1 minus XA. So I'm just trying to generalize it to some extent here. So now if we apply specifically the 2 points that we know, right? Because we were told what the concentrations were at these 2 points. So normally if you have the initial point and then you let Z vary, then we get the value as a function of Z. But in this case, we are simply given the 2 numbers. And so if you just stick in the XA2 here and Z2 there, then we can estimate the diffusion, the diffusion rate. So NA is then something we can determine from this equation. So everything is specified now, and we can just solve for NA. And so we know NA, which is the same number across the whole space. And so we can go on to then determine how the mole fraction is varying through that space. So the reason I wrote it like this is to say that if you now make XA the subject of the formula, you can see it's going to have an exponential dependence on everything else. So it's going to have an exponential dependence on the Z number. And so that tells us then that in terms of our in terms of this expression, we now have a different solution which looks more like this. Oops. So in this case, our curve is quite different. Right, so you see in the first case with equimolar counter diffusion, it's a straight line. In the second case, we've got this exponential dependence, and so it's more of a curved line like this. And it's not just one is straight and one is curved. It means that there are different concentrations in between. And if, for example, this tube was actually a pore in a catalyst particle, that means we've got different concentrations at each point. That means the reaction rate in the equimolar counter diffusion case will be quite different to the reaction rate in the component A not diffusing case. Right, so that's how we can solve for our concentration or our mole fraction and how it varies as a function of Z position. Any questions or comments there? You'll also find that I tend to write a bit of Python code just to stick the numbers in and see what things look like. So if you put the numbers in for this problem, you can see here, this is the molar flux in the non-fluxing B case, and here's the molar flux in the equimolar counter diffusion case. So it's not just that your mole fraction curves have different shapes. It's also that the actual molar flux is different. So your transfer rate of component A across these two systems is quite different. And the only thing that differed in those two cases was how component B was fluxing. Okay, so that's just to get us used to these concepts of diffusion and the interplay between concentration and flux. And so that discussion about the molar flux must be the same if this is going to be at steady state, and the fact that the concentration profile is not uniform, but it's still steady, that actually takes a fair bit of thinking just to kind of believe. So up to now, I think it's been fairly automatic. You've just been hearing just apply steady state and carry on. You have to be very careful with that steady state assumption, and you have to check that all the conditions behind it are met with before you can apply it and use it the way you think it's supposed to be used. Okay, so we'll see some examples where that's exposed a bit more. So that's problem one. By the way, in problem one, it also asks what's the mass transfer coefficient. So we haven't covered this concept as yet. We need to discuss the film theory concept, which we'll do a bit later in the course. So we'll revisit this problem. Okay, so question two just asks us to estimate the diffusivity. So if you look in the lecture playlist on YouTube, you'll see there are some comments on how to estimate diffusivity and so on. They are not detailed comments, so it's more broad comments, but the principles are the same, and so you can use the data given with this tutorial to estimate the diffusivity. Okay. So like I said, the problems that I wanted to work on were these ones, so actual mass balances. So let's read this first one carefully. So it says here, we have a perfectly mixed vessel with an initial concentration given by C naught, and it's fed by a stream with a concentration C in. So let's just draw that a bit first. So we have some vessel here. No specifics about that vessel as yet. And there's an initial concentration in there of C naught. So C naught applies here. So we can say here C at T equals 0 equals C naught. So that's some known. So specifically initially, right, at T equals 0, we have the concentration inside this space. So So here, initially, we have some concentration C0. And now we are feeding to this system. So there's a stream coming in here with concentration C in. C in. Ugh. And notice here, these two concentrations are possibly different, are generally different, right? So you've got some initial concentration in here, and you are feeding a stream in, and there's some other concentration in the stream. So you might have initially 5 moles per cubic meter in here, and you are feeding 15 moles per cubic meter in here. So those two are not so, and it's confusing because in many textbooks they use C0 and C in interchangeably. So don't be surprised if you see that. Just carefully work out for the problem you are looking at. What do they mean by that C0? Do they actually mean C in? And once that's established, the rest will follow. So those are 2 concentrations, and we can identify a third concentration as well, which is the concentration in this exit stream here. So we can call that C out, I guess. No, that's not working. So C out, right? Okay, now this is a very specific concentration. This is only at time 0. And let's generalize that a bit. Let's call C generally the concentration in here. So for all future times after 0, Ct is the function that tells us the current concentration in here. And the first piece of information was that this was perfectly mixed. So we represent that with a little mixer. So this is perfectly mixed. And now let's think about that. If this is perfectly mixed, then that means all points in this space will have the exact same concentration. So the if you take a sample from here, the concentration from that point will equal the concentration here, will equal the concentration here, and so on. I'm busy now. Okay. Okay, thank you. All right. So you've got your concentration here, which is the same at all points across that whole reactor, right? Now, if the concentration is the same at every single point in the reactor, then that's going to include the point at this exit point here. And that means that the concentration here will be identical to the concentration in this pipeline. So you can say then that the concentration in the reactor is equal to the concentration in the exit stream, right? So at least here we have one concentration involved, right? So those are the 3 concentrations of importance to us: the inlet concentration, the initial concentration, and then the concentration in the reactor or the concentration in the stream here. Right, so that's our picture to begin with. And in fact, let's just copy that. Okay. And now we want to develop the mass balance that describes the system. So we are also told, I think, the volume. So it says here the volume of the vessel is V. Yeah, okay, we don't need to write that, right? So it's V, and then the flow rates in and out are the same at Q. So volume is V and flow rate is Q. Volume is V, flow rate, and that will be volumetric flow rate. Flow rate equals Q. And now the default is that there's no consumption of the component. So when I say default, that's because you'll see later in the problem, we do something else. So by default, there's no consumption, but we might later on have consumption. So so we want to develop the material balance and sketch the solutions. So let's derive the material balance here. So we'll want to write a balance on the number of moles of the component in that system. So we can define N to be the number of moles. And so we can say the rate of change of the moles in the system, that must equal the amount of that entered here. So the entering flow rate. So the entering flow rate is going to be Q in times C in. So you agree this is the molar flow rate into the space, and then the exit flow rate is Q out times C, and C is the concentration. We can say C out, but we know C out equals C, the concentration in the reactor. So that's there. And then we can say that the number of moles in the reactor will be the concentration in the reactor multiplied with the volume of the reactor. So we can rewrite this as CV times, and then we said Q in equals Q out, so we can just replace this by Q. So we've got Q here. Right, so that's dc dt, so that's all fine. And then we can group out the Q's and divide by V. Let's think about that first. The volume of that reactor can only be divided through if it's a constant. So we have to think first, is the volume of this reactor constant? And if you've got an equal volumetric flow rate in and an equal volumetric flow rate out, then that means your net rate of change of volume is going to be 0. And in fact, more strictly, we should do it as a mass balance. So if we write a total mass balance over that reactor, we can say dm dt on that vessel is equal to, and then we can rewrite that as d rho times V, right? So density times the volume, that's going to be the mass in that reactor. And then our inlet flow, so assuming the same density here, so density times that volumetric flow rate, so that's rho times Q, okay, that's Q in, and then minus rho times Q, so that's the exit flow rate. So we can, of course, cancel the densities. So if density is not changing with time, then the densities can cancel. Then you've got Q minus Q, so that means dV dt is 0. So dV dt is 0, so that means V is constant, so we can divide V out as a constant here. So we can just say this divided by V, Q divided by V times C in minus C. Right, so that's the material balance for the first situation, for the first, well, not even a variant, all right? So for the problem as it is, that's the material balance. And then I did actually simulate this. This is a very simple one, but I simulated it, not here. So where is that? Here. Yeah, so I started first writing up these problems as a so-called warm-up modeling problems. So here, if you look at this one, so no variance, Q in equals Q out and all that. So everything we just wrote there. So the same material balance. And then we just, some Python code, and I just stuck some arbitrary numbers in there. And so here we have an initial concentration of 20, and your inlet concentration is 10, and then your flow rate and volume are just chosen there. So you can see if you simulate this using the ODE integrator, you start at 20, and then the concentration drops over time, and it ends up on 10. So the reason for that is as time goes on, your component, your fluid in here is being washed out of the system. So initially you had a certain amount of fluid in that reactor and it had a certain concentration there. And then you started feeding a certain other stream in, and that had a different concentration in that inlet stream. And so what's going to happen is slowly the fluid that's currently in the vessel is going to wash out. So it's slowly being replaced by the fluid coming in here. So this fluid is, and it doesn't happen all at once. So we are not, if this is 50 cubic meters, our flow rate here is not 50 cubic meters per microsecond or something. It's not instantaneously replacing all of the fluid in this reactor. It's taking some time that each element of the fluid is exiting, and sometimes it's not the old fluid, it's part of the new fluid, and so on. We say all this much more professionally in other places, but for right now, we'll say it that way. And so it's slowly being replaced. This original, if you like to think of it as the original population in that reactor, is slowly being replaced by a new population. And that new population has this new concentration C in. So our concentration here slowly becomes more and more like your inlet concentration. And you can see that here, originally we were at 20, and then as time has been going on, that high initial concentration has been replaced by the concentration that's coming in with the inlet stream. Okay, any questions or comments there? Okay, and yeah, by the way, I can't fit all the names on this panel, so don't feel afraid to just unmute yourself and say, yes, I have a question also. Okay, so that's the first simple situation. The next thing that we have in this spec is a variation on that, which is to say your exit flow rate is gravity driven rather than being equal to the inlet flow rate. So let's, maybe we want to draw it a little differently. So if you have a gravity-driven exit stream, right? So we've got some level in here, in this vessel, there's some level. So we are feeding in at a flow rate Q in. And then the height here is going to dictate the exit flow rate Q out. By the way, I forgot to check the third years are writing my test. I just want to check here. Okay, no issues on the test, hopefully. Okay, so you've got Q in and Q out here. So two volumetric flows, and now the flow rate in a gravity-driven situation is going to depend on the height in that vessel. Let's see, where's my scratch pad? Here. So in a gravity-driven flow, you have Q out is going to be proportional to the square root of the height. So K times square root of the height. And so the height of the liquid there, right, the height of this liquid is of course proportional to the volume. So instead of saying height, we can say volume here, right? So that's our exit flow rate. And now because we can't guarantee that we were at the nice steady state value, right? This volume could be anything, right? We do specify an initial volume, and I think we said 15 cubic meters or something like that. And there's no guarantee that the number that you put in here is going to give you a Q out, which is equal to Q in. So generally speaking, in this situation, Q out is not the same as Q in. And so we can no longer just say dV dt equals 0. So dV dt is now Q in minus Q out. Well, it's minus K times square root of V. Okay. Now, this Q in is some fixed constant, or, well, we could vary it, but we're not really going to in this problem. We are going to say there's some fixed flow rate that we are feeding at here, and then the volume will change depending on how fast we are feeding here and how fast it's exiting here. And maybe we can draw a slightly different situation here. So if you have a very low flow rate initially, let's say you had a very you had a low initial you had a low initial volume in that reactor, then you see your exit stream initially is going to be low, right? There isn't much driving force to push fluid out here. So you have a low initial exit flow rate and a fixed, not necessarily low inlet flow rate. So your volume is going to rise here. And then the volume keeps rising until it's high enough that this poses significant driving force, that you've got enough pressure being exerted by this fluid on this point that the flow rate here becomes high enough that it equals that flow rate, right? So what we expect to happen is that the volume will change with time. Right? So if you start with a small amount here, it's going to increase, and then it will level out. It will increase and then level out at the point where the height gives us a flow rate that equals that flow rate. And you could say, well, why must it level out? Why can't it just keep rising? And that's because if you go past that height, right? Imagine now you are on the other side of that. Let's say we started at a very high volume in that reactor. So maybe the thing was much bigger then, and so you started out with a very high volume, right? Then it might be the case that your supply rate in here was actually lower than the flow rate out here. So your height was so great that you had a very strong driving force, and so your exit flow rate became quite high. So you had a high flow rate there and then a low flow rate there. That means your level is going to drop, but that level will drop and then it will reach some point where the two balance. So it might end up doing something like this. So if you start from a high value and come down, right, the volume is going to drop, and then it will reach a point where the two are equal, right? So that's what can happen. So that's a situation where we have a nice stable steady state. Not all systems have a stable steady state. Sometimes they have an unstable steady state. Sometimes they have no steady state. Sometimes you get sustained orbits. Sometimes you have multiple steady states, and then you have to, and in fact, we do all that in the, you can watch my other playlist in Reactor Fundamentals course. We cover those situations. So anyway, here, those are some things that can happen. But the point of all that is that we can't trust this volume to be constant anymore. And so we have to now retain this equation here. And so if we go back to the balance that we wrote here, well, in fact, this was the version where volume was constant. So we have to go back to here. So our material balance on the component, where we wrote this as CV, now we have to expand this term. So we can write this as C times V. So we have to use the product rule of differentiation here. So we've got, if we just apply product rule here, it's going to be C dV dt plus V dC dt. And now for dV dt, from the, this basically comes from the total mass balance, as we said earlier. So dV dt is equal to this stuff. So we can just replace it here. All right, and then we can see our new balance now looks like this. So this is the balance in this situation. And we might as well just take this thing across to this side. And here, see in nothing cancels here. Okay, so that's our new balance. And we have to acknowledge here, V is a time function. So everywhere where you've got V, you can emphasize that it's a time function. Okay, and we need to solve this equation. We can't solve it without knowing V as a function of time. So if you want to divide by this V, you have to write it like this. And then you that. Okay, so that's the balance in the second situation. And we have to solve that equation simultaneously with this one. So this is the material balance in case 2. So in case 2, with that simple change, we now have to integrate an additional equation, right? Our total mass balance. So don't talk about a volume balance, please, right? You can't do a volume balance. Volume doesn't stay constant. You have compressible gases and so on. So call that a mass balance, right? So when you write dV/dt, remember that there's a density behind this and that it's actually mass that we are talking about. So mass is the thing we can say is conserved. So anyway, we've got a total mass balance, and then we've got a component mass balance as well. And to solve this component mass balance, you have to integrate that simultaneously with the volume balance. Okay. Now, I actually feel like spending a bit of time on just revising what it means to solve differential equations and so on. But maybe let's just pause there. Any questions or comments so far? So let's talk about solving differential equations. And let's just consider it in the abstract first. So let's say solving differential equations. Solving differential equations. So if let's take a simple scalar case first. So let's say dy dt is some function of t and y. That's our differential equation. And we want to know y as a function of time. So let's think about what this equation means, what it's telling us. And one of the reasons I think people don't really get differential equations is because there's this automatic tendency to want to go and solve the equation. And you see, when you look at a differential equation, you have to appreciate it in its current form. It's an equation of change. It's telling us how something is going to change in response to something else. So this function f tells us how the current time and how the current value of y are related such that y changes according to that relationship. It tells you the relationship between the change in y and y itself. And you can imagine situations like that, like the rate of increase of a population that depends on the size of the population. The reproduction rate does depend on how many members are busy reproducing in there. So a differential equation can depend on its own variable here. So with that in mind, with seeing it as an equation of change, let's not talk about analytical solutions straight away, right? That kind of distracts from understanding a differential equation. In fact, the numerical form of solving it gives us more of an appreciation of a differential equation. So let's imagine a numerical solving of that equation. So let's say somehow we knew some starting point, right? So we are talking now about t and y, and we have some initial point. So we have a t naught and a y naught, t naught, y naught. Yeah. T naught, Y naught. Now, if you look at this equation, it's telling us that if you give me the time and the value of Y, I'm able to tell you the gradient dy dt. Now we have a couple. We have t and y, right? So we know a number. We know a t value here, and we know a y value there. And so we just stick those two numbers in here. So we stick the two values in here, and we evaluate this function, whatever it is. So like here, it's some function, and we evaluate that, and it gives us some number. So this, yes, it's a function, but it's returning a number for us. So that number is nothing but the gradient in time. So we interpret that number as a gradient. So for example, if it's a value of 0.5, so maybe it's a gradient that looks like that. So it's telling us that y is changing in that way. It's y is changing with that gradient. So it's telling us at this specific point here, y tends to change with time like this. And now we can't trust that it's always going to carry on like this. We can't say, oh, it's going like that, so let's just maybe there. So we can't trust that this is going to stay the same all the way along this line, because the moment let's say we move along this line and we've got a new point now. So let's say we've got a new point here. Now your value of y has changed a bit, and your time has also changed a bit. So now you've got new numbers. So what we want to do then is stick these new numbers back in this equation, and then that will give us a new gradient. And maybe the new gradient is something like this. So maybe the new gradient looks like that. So now we have to step forward on that point. So maybe that gives us a new point here. And then we re-estimate. So that gives us a new point. And then we recalculate the number, and that gives us a new gradient. So maybe that's there. And so you see these points that we are discovering, right? We are using the statement of change to figure out how y is going to evolve over time. So if you like, it's a statement of evolution. It tells you how y is evolving. So when you understand that, all of differential equations, including partial differential equations, becomes quite a straightforward thing. So please, I know this all sounds very straightforward and it's obvious and you've already seen this, but I noticed the moment we get to PDEs later in the course, everybody just blanks out and they don't want to deal with it. And it's as easy as this. It's just that you currently have some state, some initial value, and you have a statement of the change in that value. You have basically a nice little magic box here, right? This function is your nice little box, your bit of magic that tells you, if you know what you are currently, I can tell you how you are going to change, right? And that's certainly what fortune tellers do, right? But of course, ours, we say we are more rigorous because it's all based on our physical laws and so on. So anyway, we now have this magic box that tells us how things change. And if we take it one step further, so we are saying, because of the method, the magic of numerical methods, if we know how things change, we know then how to predict the next values. We know how to step forward a little bit. So if we know the change is like this, we know that we can step forward a little bit and see what the next stage is, and then step forward a little bit more, and then that's the next stage, and so on. So that's what we mean by this differential equation. And the reason I brought this up here is because you see now we've got two equations that need to be solved simultaneously. And I wanted you to appreciate that it's impossible to do this now with just one equation, right? You've got an unspecified time function here. Volume is changing with time. And it's changing not in some specified way. It's not like someone said, okay, in this column, we shall make the volume change. It will be 50 cubic meters at the start of the day, and then it will go parabolically down through 49, 70, whatever. So it's not as if we are specifying, it's not like V of t is known initially. So V of t does depend on its own set of physics, and so we have to solve this equation together with this one if we plan to have a solution. And so that introduces the idea that you may have coupled differential equations. And so to show that, let's go back to this abstracted case. And let's say we had two coupled equations. And in fact, I'm going to remove the time dependence here and just show this is y1. And let's say there was a second state variable in the system. So there was a y2 as well. And so y2 then followed its own laws. So we had another state variable, y2, and that was governed by some other function, f2. So we have simultaneously these two equations. You can't solve either one of those independently, generally speaking. And so how do we modify our calculation scheme? Well, it's in fact a similar concept as we've already talked about. So you've got your time, and you've got your two functions, y, let's just say y. And now let's say we have specified at some t0, at some initial time, we happen to know the values of y1 and y2. So y1 happened to be this value, and y2 happened to be this value. And then you see we've specified three numbers now. We've specified time, y1 and y2. And you see here, that's all we needed, right? If we know y1 and y2, we can go and stick a number in here. We can stick it in this function, and this function will give us a number out. Similarly here, y1 and y2 are known. We stick it in this function, and that gives us another number out. And so maybe the gradient here looked like this, and then maybe the gradient here looked like that. And so we would step forward, and when I say step forward, we can say delta y1 equals f1 times delta t. And it's going to be So delta y1 equals f1 delta t. So the change in y is f1 times delta t. Right, so if that's the gradient, if dy1 dt, and of course this comes straight from your fundamental theorem of calculus, so dy dt times delta t is delta y1. So we've got the delta, so we can increase by our delta amount, so that gives us new values, and so it can shift, so we can span out the solutions there. And the point is, for each step forward, you need to get the updated numbers. In fact, I jumped a bit there. So we step ahead to the new values. So we get new numbers for both y1 and y2. And then we stick the new numbers in both these functions. And then we get, we step forward again. So we get two other numbers. And then we keep doing that. And so we span out the solution in that way. So that's how these things work, right? You look at the equation and you check whether you have a dependence on a quantity that is changing in time. And it might be that you are fortunate enough to know how it changes with time, so you have the function already. In that case, you don't need to do that. But if you don't know how this is working, and you only have a statement about how it changes in time, then you have to solve these simultaneously. I say that, but in this case, you can actually solve this equation independently. This equation doesn't depend on C. So you can solve this equation independently, and then you get V of t, and then you can just stick V of t in here. right? But if you had a situation where dV dt also depended on the concentration itself, then you would have to solve these two equations simultaneously, as we've just described. Okay, any questions or comments there? Right, so we have these two equations now, and in the solution, I'm showing that variant. No, actually, that we actually went into the second variant, not the first one. So all that development we've described, and here we are showing volume as it's changing. So for these assumed constants, in this case, I set the gravity-driven exit constant to be this value, and 15 to be the initial volume. So you can see the volume drains. So this was a high volume initially, and then it reaches its steady state value at that number, and then the concentration changes, and you get a different concentration compared with the first case. So the first case had, well, actually it's close to, but it's just a coincidence. Yeah, it's not exactly the same there, but yeah, it changes when you incorporate that kind of variant. Okay, for the second variant, or well, rather it was the first variant, we are told here your component is actually being consumed in a reaction, and the rate of consumption of that component is proportional to the concentration itself. So the rate of consumption is proportional to the concentration. So your equation would look like this, right? So here's what we had before: flow in and flow out. But now our component is also disappearing in this reaction, in this consumption. So we have to, so we show it's proportional to the concentration like that. And so the only change here is that we have an additional term like this. And if you apply that, then you'll see you get a different answer to the first case. Okay, so that's your first warm-up problem, right? Your perfectly mixed vessel. In the next problem, you've got a two-compartment cell. So I'd like you to work on that one by yourself. So let's just read it though. So here you have a two-compartment cell separated by a permeable membrane. So again, just to sketch that out. So you've got two compartments separated by a membrane. Yeah. And that's just 2 millimeters. 2 millimeters. And these two compartments have some fluid there, and they have a certain initial concentration. So you've got Ca1, Ca2. And then the default in this problem is that they are perfectly mixed. So you've got a two-compartment cell separated by a permeable membrane of thickness delta. So it doesn't say 2, it says delta. So the thickness is delta. And then initially we have concentrations C1 and C2. I said Ca1 and Ca2, never mind. And these concentrations are the same at all points across the cell due to perfect mixing. So again, we've got perfect mixing involved. So you've got a mixer in each case. So because of perfect mixing, your concentration is the same at all points in here. So your task is to develop the material balances and find how concentration changes with time. And that's a fairly straightforward exercise. However, the more interesting part is in this variant where the agitators are removed. So, and that's obviously trying to say, what if you can't assume perfect mixing anymore? And that introduces some really interesting behavior. So I'd like you to spend some time thinking about that. Try to sketch out your solution, develop your material balances, and see if you can code up some arbitrary numbers. I know you are the class with the new version of the Applied Computer Methods course where there's more time spent on Python. So I'm assuming everyone is quite Python skilled. Can I assume that? Anyone want to comment on their Python skills? No takers? Well, yeah, it's not a requirement for this course to write Python code. I do it. You'll see it in the examples, just because it helps you understand the results when you can see the graphs. That helps you believe the solution and the claims we make better. So in this course, because we have no requirement on the programming side, I must just check. I don't think there's any. Because there's no requirement, when I show the code and all that, you can just skip to the figures and see that it's making sense in terms of the theory. So don't stress Python. But definitely, if you do spend a bit of time getting used to it, it's going to help you a lot in the upcoming courses. Okay, I guess that's it for today. Thank you. See you next time.